All right, tonight what we're going to be talking about are the exceptions to the octet rule and when you're drawing Lewis dot structures. There are going to be three focuses of tonight's unit, and that is for reduced octets, expanded octets, and those that have charges. All right, so first what we're going to talk about is reduced. And there are two elements in this class that you're going to need to know that have a reduced octet. So reduced means less than, and octet means 8. So these are the elements that want actually less than 8 electrons. And these are always the situation. So boron always wants 6 electrons. And if it wants 6 electrons as opposed to 8, what that means is that you are only going to be making 3 bonds with that boron. Hydrogen only wants 2 electrons, which means you are only going to be making 1 bond with every hydrogen. And these are always the case, okay? So these, you always have that, okay? So boron will always want 6 and hydrogen will always want 2. So let's just try a straight out example of this. When we are going to be drawing the BH3, we first, as always, need to figure out the number of electrons. So boron has 3 valence electrons. Hydrogen has 1 valence electron, but we have 3 of them. So what that means is we have a total of 3 plus 3. So 6 electrons that are at our disposal. There you go. All right, so as with the previous drawings, we need to put boron in the center because it's written first, and you're going to surround it by your hydrogens to try to make it as symmetric as possible. Hydrogen each has 1 valence electron, and boron has 3. All right, so now looking at this, we're going to bond these guys. Right? You remember you bond every lone electron to make them partnered up to make a bond. And so if I were to redraw it, I'm going to put boron in the center. I'm going to have my hydrogens symmetrically surround it. And then every time I have a bond, I'm going to draw a line. So between the boron and the first hydrogen that I'm going to be focusing on, which is this guy, I see 1 bond, 1 line. Between the boron and the hydrogen up above, I see another 1 circle. And then between the boron and the hydrogen on the left, I see another. So this one has 3 single bonds. I then need to check which ones have lone pairs. None of the hydrogens have a lone pair, and boron does not have a lone pair. So when I'm counting, I now need to make sure that everybody's happy. So boron wants 6, remember, so it would have 2, 4, 6 electrons. Every hydrogen only wants 2. So looking at that, I've got 2 for this guy, 2 for that guy, and 2 for that guy. So far everybody's happy. And then the last thing I need to do is check to make sure that I only used those 6 valence electrons that I previously had talked about. So this would be 2 with the orange line, 4 with that yellow line, and 6 with that purple line. So this would be the true structure because I used only the electrons I was allotted, and everybody's happy. All right, another exception is not just reduced, but expanded. And as you go lower or further and further down the periodic table, they become more and more likely to be able to expand their electron shell, which means that they can take more than 8 electrons. Now, these guys are sometimes they will have an expanded octet, sometimes they will not. In this class, we will always tell you when it will be expanded and when it will not be expanded. So the 2 that you need to know for this class is sulfur and phosphorus. Sulfur wants 12 electrons, which means that it will form 6 bonds. So instead of having 8, it wants 12. And phosphorus wants 10 electrons, which means it can form up to 5 bonds, as opposed to 4 bonds or 8 total electrons. So whenever it's expanded, we will tell you that it is expanded or that it is an exception. We will probably tell you more that it's an exception because then we are testing on whether you know that it's expanded or not. In sulfur's case, we still need to count how many electrons that they have available. So sulfur has 6 and we have 1 of those. Fluorine has 7 and we have 6 of those. So total that is 6 plus 42. So we have a total of 48 electrons available. All right, so now when you are trying to do the valence electrons, or when you're trying to draw the structure, once again, you want to draw the first one in the center and surround it as much as possible to make it asymmetric. So with this guy, I'm going to draw F here and down here and over here and over here. And I could draw the F over to the side like this, and I actually am going to do that for right now. All right, so sulfur has 6 valence electrons, so I'm going to do 1, 2, 3, 4, 5, and 6. So that would become a lone looking. F has 7, so it's going to look like this. All right, so everything has 3 lone pairs with 1 lone electron. All right, so this is our structure. Now what I'm going to try to do is bond any single electron with anything else. We've got 1 and 2. And here's my issue. Right now, if I were to bond, let's say, the 2 fluorines to the left, they have nothing available to bond with anything else. As opposed to the structure that says SF6, I know that SF6 has to be entirely touching, something needs to be touching in that entire compound to something else. I should never have to pick up my pen to go to a new compound. They are all a part of the same compound. So knowing that, I know that this structure is not how I can handle it. Well, and here's the trick. So when you have sulfur as an expanded octet, what you need to do, and I'm going to actually delete absolutely everything, what you need to do is you draw your sulfur, and sulfur, when it is expanded, remember it can form those 6 bonds. So what I'm going to do, as opposed to connecting my lone pairs like this, I am going to actually allow those lone pairs to not be lone pairs anymore, but lone electrons, and I'm going to do it in yellow. Make it easier for you guys to see it. Instead of being a lone pair, they are going to now be lone electrons. So what does that mean? It means that these are available for bonding. So it would be 2, 3, 4, 5, 6 positions as opposed to 6 valence electrons with only 2 lone electrons able to be bonded. I now have 6, and this only occurs when it is expanded. So now looking at that, instead I'm going to draw a configuration where F's are all surrounding it. All right. All right, so I took the time to draw all my F's, and now I notice that I have 1 lone electron that's available for bonding on every F and 6 lone electrons on sulfur that's available for bonding. So now I'm going to connect all of my F's to that sulfur. Notice now everything is bonded to something else in the same compound. They're no longer free-floating, so I am good on that. Now I need to just redraw my structure. So I am going to erase this because I ran out of room, and I am going to redraw my structure. So I'm going to draw S in the center, surrounded by my fluorines. Okay, now I'm going to draw all my bonds. I notice that each sulfur is connected by a single bond to every F. So I'm going to draw all of those, which means that S now has those 6 bonds. And now I'm going to draw all the lone pairs on all of the elements. Each F has 3 lone pairs, so I'm going to draw those now. And now that I've drawn everything, I need to count to make sure that everybody has what they consider to be happy, either 8 or in sulfur's case 12. And then I've only used my 48 electrons. All right, so let's start accounting. Sulfur has, I count off all around, and it has 6 bonds. So 6 bonds means it has 12 electrons, so it's happy. Each fluorine has 4 lines, which means 8 electrons, so they are happy as far as that goes. Now, as far as total electrons that I was able to use, I can use 48, which means that I need 24 lines. So I'm ready to count, okay? So here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So I've used up all the electrons I can. I have also made everybody happy, so I know that this is my final structure. And the final exception is going to be charges. There are two types of charges that you can have. You can either have negative charges or you can have positive charges. Because you gain or lose electrons to make a charge, what you're going to be doing is if you have a negative, you actually gained an electron. When you have when you have a positive, you actually lost an electron. Okay, so what you're going to do is if you have a negative charge, you're going to add that many electrons, and when you have a positive, you're going to take away that many electrons. After you are drawing the new structure, you put it in parentheses and give the charge outside of parentheses. All right, so the example that we're going to do is we're going to do oxygen. Oxygen has 6 valence electrons, and we have 1 of them. We have 1 hydrogen, and it has 1 valence electron. And then now what we need to do is deal with that negative charge. That negative charge is a -1, so I actually added 1 more electron than I had originally with just OH. So I've got 6 plus 1 plus 1, so I have a total of 8 electrons that I can draw. All right, so the next thing that we need to do is we need to put oxygen in the center, and then we're going to surround it by all the hydrogens. Well, we only have 1 hydrogen, so it's not a big deal. I'm going to give everybody their normal valence electrons. So oxygen has 1, 2, 3, 4, 5, 6, so that would form a lone pair, and that would form a lone pair, and hydrogen would have 1 valence electron. All right, so now I need to deal with this extra electron that I gained from that negative charge. What you want to do is you always want to add that extra electron, which I'm going to do in orange, to the most electronegative. Why? Because you are gaining an electron, and who's going to want that electron most? That would be the most electronegative. Now, looking at your periodic table, you know that F is the most electronegative element, so the thing that's closest to it is oxygen, so I'm going to add that extra electron to that oxygen. Now I have two dots at the bottom of my oxygen, so I'm going to make that a lone pair. All right, so now I've dealt with all of my electrons, and now I'm ready to bond. So I see that each of these has 1 lone electron. I'm going to bond those. Now I'm going to redraw my structure. So I have an O with an H. I'm going to now draw the bond that exists between them with the 1 circle. This would be 1 single bond, which represents 2 electrons. And now I'm going to draw the lone pairs around every single element. Hydrogen does not have any. Oxygen has 3 because it gained that electron from the -1 charge. Okay, and now I'm going to put brackets around it, and I'm going to give it its charge of a minus. You can write a -1 if you would like. Why do you write it? You write it because you need to tell everybody that somehow you had gained an extra electron, and that's why it works, as opposed to you just drawing it without it and somehow you created an electron out of thin air. All right, so now we're ready to check. Hydrogen in this case has 2 electrons, so it is happy because remember, it always wants a duet or 2. We have oxygen has 4 lines attached to it, so that means that it has the 8 that it always wants, which is the octet. Now you need to check to make sure you only used 8 electrons, which would be 4 lines. So I'm counting 1, 2, 3, 4 lines. So I'm good to go. I know that this is the true structure of what OH minus would look like. All right, so tonight what you have done is you have learned about the exceptions, which means a reduced. So you have your hydrogen and your boron. You have your expanded, which in this class is phosphorus and sulfur. And then you have your charges, which is your negative and your positive. Remember, if you got a negative, you gained an electron. If you're positive, you have to take away an electron. Have a good night.